Welcome back to Physical Science 101. This is our fourth and final lesson of Unit 5, Electricity and Magnetism. So far we've been talking about electricity, and today we're going to talk about magnetism. We're going to start with the magnetic field. The magnetic field is created by moving electric charges or electric currents. Unlike the electric field, which emerges from positive charges and converges on negative charges, magnetic field always forms closed loops around the electric currents. So as you see in this diagram, we have a wire carrying a current. The magnetic field forms closed circles around the wire. That means if we have a compass on one side of the wire, that compass, which will align itself with the magnetic field, will point in one direction on one side and in the opposite direction on the other. Let me demonstrate that for you. Okay, here I have a compass, and the compass needle points in the direction of whatever magnetic field there is. Right now it's pointing north, because the only magnetic field around is the Earth's magnetic field, which is pointing from south to north. That's how a compass works. It aligns itself with the Earth's magnetic field, pointing from south to north. But the compass only works when it's the only magnetic field around. Now what I'm going to do is I'm going to add another magnetic field by having this wire with a current running through it. Okay, right now there's no current because my switch is open. But here's the battery. The current flows in the wire, into the switch, and back to the battery. So as soon as I close this switch, there's going to be a current flowing through the wire. And so when I do that, watch what happens. The compass is now pointing sideways. It's now pointing in that direction. It's now pointing sideways, because the magnetic field from the wire is pointing sideways. So the electric current's going that way, and the magnetic field is sideways in that direction. So it's pointing in that direction. But now watch what happens if I put the compass on top of the wire. If I put the compass on top of the wire, now the compass is pointing in this direction. So the magnetic field from the wire is pointing in this direction now. So the magnetic field from the wire, when a current flows through the wire, the magnetic field points in that direction on the bottom and in this direction on the top. That's because the magnetic field of the wire is making closed circles around the wire. Oops. Is making closed circles pointing in that direction, coming up and going around. So the magnetic field around an electric current makes circles around that current. Okay, we saw a couple of things there. The first is that it was the electrical current that was creating the magnetic field. There was no magnetic field when there was no current. The second is that the magnetic field pointed in one direction on one side of the wire and in the other direction on the other side of the wire. Or in other words, the magnetic field was circling the current. So whenever we have a current, the magnetic field created by that electrical current circles and loops around that current. Now we also know that electric current flows in circles and circuits. So let's look at the magnetic field of a circle of current. Here I have a small circle of current, and the magnetic field created by that circle of current loops around the current. In this case, the magnetic field is entering the loop on the bottom and exiting the loop on the top, so that there is a side where the magnetic field goes in and a side where the magnetic field goes out. The side where the magnetic field comes out we call the north side, and the side where the magnetic field goes in we call the south side. And so we call this a dipole. meaning that there are two poles. There is a north pole and a south pole to the loop. We can put a bunch of loops of current together in a cylinder, and that cylinder of wire loops we actually call a solenoid. So a solenoid is a cylinder with a wire wrapped around it many times, and that makes an electromagnet. When we connect the solenoid to a battery, a current will flow, and we will see a magnetic field that has both a north pole and a south pole, exactly like a bar magnet. So a bar magnet has a north pole where the magnetic field comes out and a south pole where the magnetic field goes in, and a solenoid has the same thing. So both a solenoid and a bar magnet have the same kind of magnetic field, same direction, but same two poles, north pole and south pole. But the electromagnet also has the benefit that we can turn it on and off. Let me do a demonstration for you. Okay, so what I have here now is a solenoid. It's a cylinder of wires. So we have these wires wrapped around in a cylinder, and I connect those wires to a battery and a switch. So when I turn this solenoid on, it's actually going to become a magnet. It's going to create a magnetic field, and it's going to have a north pole and a south pole, just like a bar magnet. Let me start off with the bar magnet. Here I have my bar magnet. The red is the north pole, the blue is the south pole, and what happens is when I bring the bar magnet next to the compass, notice the compass is pointing away from the north pole because the magnetic field of the bar magnet is going out of the north pole and coming into the south pole. So if I turn the magnet around, now the compass is pointing towards the south pole of the magnet. So once again, the magnetic field is coming out of the north pole of the magnet and going into the south pole. So the compass will point away from the north pole because the magnetic field is going out of the north pole, and the compass will point towards the south pole because the magnetic field is going into the south pole. So that is a bar magnet. And actually I can also put the bar magnet sideways. When I put the bar magnet sideways, look what happens. The compass is now pointing in that direction because the magnetic field comes out of the north pole, turns around, and goes into the south pole. So over here, the magnetic field is actually in that direction. Now that is our bar magnet. I can actually do the same thing with our electromagnet, except now I can also control it. I can also turn my magnet on and off by closing the switch. When I close the switch, the solenoid has now become a magnet. So this must be the north pole because the magnetic field is going out of the north pole and the compass is pointing in that direction. I can turn it back off, and now this is no longer a magnet. So the solenoid is actually an electromagnet. It's a magnet that I control with my switch. So I can turn my magnet on and off. I can't do that with my permanent magnet. My permanent magnet is always on, but my solenoid I can turn on and off. So this is the north pole of the solenoid. Magnetic field's coming out, so the compass is pointing that way. If I turn it around, this must be my south pole because the compass is now pointing towards the south pole. So the magnetic field is coming out of the north pole and going into the south pole. So this electromagnet is just the same as a bar magnet, except that I have control over it. And once again, I can also turn it sideways, and we have exactly the same situation as we had with the bar magnet. The magnetic field comes out of the north pole, goes down this way, and into the south pole. Now I have a few questions for you. A current-carrying wire always has a magnetic field with closed concentric field lines around the length of the wire, B, a magnetic field with field lines parallel to the length of the wire. C, an electric field but no magnetic field around the wire. Or D, nothing in the space around the wire. Okay, think about that. Come down on an answer. Make sure you have an answer. Pause to give yourself some time to think. And then when you have an answer and you're ready to hear the correct answer from me, hit play. The correct answer is A. A current-carrying wire always has a magnetic field with closed concentric field lines around the length of the wire. That is the magnetic field of a current. The magnetic field loops around the current. There are closed loops around the wire that's carrying the current. The source of a magnetic field is A, having more north poles than south poles, B, having more south poles than north poles, C, moving electric charges, or D, the separation of positive and negative electric charges. Once again, think about this, pause, give yourself some time to consider, and when you have an answer, hit play, and I will tell you the correct answer. The correct answer is the source of a magnetic field is C, moving electric charges, otherwise known as an electric current. So moving electric charges are an electric current, and electric currents create magnetic fields. Let's talk about those first two answers, having more north poles than south poles or having more south poles than north poles. That can't happen. It is a dipole, and for every north pole there is a south pole. So there are just as many north poles as south poles, so A and B can never happen. And D, the separation of positive and negative electric charges, that is what gives us an electric field, not a magnetic field. The source of a magnetic field is C, moving electric charges, or an electric current. Last question. If you reverse the direction of the current in a wire, then the magnetic field around the wire will A, disappear, B, have a reversed north pole direction, C, become stronger, D, remain unchanged. Go ahead and think about this. Think about what the best answer is, and then when you're ready, hit play, and I will tell you the answer. The correct answer is B, have a reversed north pole direction. So if you reverse the direction of the current in a wire, then the magnetic field around the wire also reverses. So if you were to take, say, a wire and turn it around so that the current flows in the opposite direction, the magnetic field will turn around with it. So that will reverse your north pole and your south pole. So the correct answer is B, have a reversed north pole direction. That is another thing that you can do with an electromagnet, is you can just reverse the current and you can swap out what is the north pole and the south pole. Okay, we talked about magnetic field. Let's talk about magnetic force. A magnetic field is created by magnetic dipoles, and a magnetic field exerts a force on magnetic dipoles. This is what we saw before with gravity and with the electric force. With gravity, the gravitational field is created by mass, and the gravitational field exerts a force on mass. The electric field is created by electric charge, and the electric field exerts a force on electric charge. So similarly, since the magnetic field is created by magnetic dipoles, the magnetic field exerts a force on magnetic dipoles. Now there are two effects here to be aware of. The first is that the magnetic field will tend to align a magnetic dipole with the magnetic field. This is how a compass works. A compass is a small magnetic dipole, and it's free to rotate. So if we leave it free to rotate, that compass will align itself with whatever the magnetic field is, wherever it is. Normally, at least the strongest magnetic field around is the Earth's magnetic field, so a compass will tend to align itself with the Earth's magnetic field. But there are many situations where a compass will not point towards north because there's another magnetic field around, and the compass aligns itself with whatever that local magnetic field is. So the first effect that a magnetic field has on magnetic dipoles is to align the dipole with the magnetic field. It will cause the magnet to turn so that the magnet's north pole is aligned with the magnetic field. Then, once the magnetic dipole is aligned with its north in the direction of the magnetic field, then the dipole will be attracted in the direction of the stronger magnetic field. So a magnet will have two effects on another magnet. First, it will rotate the magnet so that the magnet is aligned with the magnetic field, and then it will attract the other magnet to the stronger magnetic field. Now we can turn this attraction into repulsion if the dipole is forced to be aligned opposite the magnetic field. In other words, if we don't allow the magnet to turn, then we can turn that force of attraction into repulsion. Let me do some demonstrations for you. Okay, here I have two magnets. The red sides are the north sides, and the blue sides are the south sides. Okay, let's look at the forces between these two magnets. I'm going to put this magnet sideways, and I'm going to bring the north pole of this magnet in towards that magnet. So this is the north pole of the magnet, so the magnetic field is pointing out. So we have a magnetic field pointing in that direction. Now, two things are going to happen. The first thing is that this magnet is going to turn to align its north pole with the magnetic field. So that is the first thing that's going to happen. And then the second thing that's going to happen is once the magnet is aligned with the magnetic field, it's going to be attracted to the other magnet. So let's do that again. So you see that two things happen. First, the magnet turns to align itself with the magnetic field, and then it is attracted to the other magnet. So one more time. And let me turn it sideways like this, and it'll turn the other way. Okay? So the first thing that happens is that the magnet will turn itself to align its north pole with the magnetic field, and then in that situation, it's attracted to the other magnet. So turn and attract. Turn and attract. Another way of looking at that is that the magnet will turn so that its south pole is facing the north pole. Okay, it will turn to make its south pole face the north pole of the other magnet. So the south pole is attracted to the north pole. It will turn so that the south pole is facing the north pole, and those two are attractive. Now we can also make these magnets repel, but in order to do that, we have to prevent this magnet from turning. I'm going to turn it so that its north pole is facing this north pole, and I'm actually going to use this pin right here to keep this magnet from turning. So now I have a north pole facing a north pole, and if I keep that magnet from turning, then we actually get repulsion. Now notice it still is trying to turn, but I'm preventing it from turning with the pin. So the two north poles of the magnet repel each other. But in order to get those magnets to repel, we have to keep this one from turning, because what will naturally happen is that that magnet will turn and then be attracted south pole to north pole. So there you see the effect of the magnetic field created by one magnet on another magnet. Here's a quick question for you. The north pole of a compass needle points in the direction of A, the local magnetic field, B, opposite the local magnetic field, C, of the Earth's north pole, D, of the Earth's south pole. Now think about it. What is the best answer here? Pause, and when you're ready to hear me talk about the correct answer, hit play again. The correct answer is A. The north pole of a compass needle points in the direction of the local magnetic field. In many cases, the direction of the local magnetic field is the direction of the Earth's north pole. That in the absence of all other magnets, the Earth's magnetic field will be the biggest magnetic field around, and the compass will point in the direction of the Earth's north pole because the Earth's magnetic field points towards the North Pole. However, if there is another magnet or an electrical current around, then that will create another magnetic field that could be stronger than the Earth's magnetic field. So the compass needle always points in the direction of the local magnetic field. Often that is in the direction of the Earth's North Pole, but not always. So A is a better answer than C. So far we've talked about electromagnets, but we haven't said much about permanent magnets. So what's going on inside of a permanent magnet? If I've said that electric currents are the source of magnetic fields, where's the current inside of a permanent magnet? The answer is in the atoms that make up the permanent magnet. Electrons, protons, and neutrons are all, by themselves, tiny magnetic dipoles. The electrons orbit around the nucleus. That also makes a magnetic dipole. So atoms themselves are all tiny magnets. Mostly, however, these tiny magnets are randomly oriented so that the magnetic fields from these magnets cancel each other out. However, in some materials, such as those containing iron, cobalt, and nickel, all the tiny dipoles line up to make a big dipole. And when that happens, that's how you get a permanent magnet. So all of the tiny magnets throughout the permanent magnet line up to give you a big permanent magnet. So the electron is permanently orbiting around the nucleus. The electrons and protons and neutrons are all constantly spinning, so we have a movement of charge there. So the consequence of this is that if you were to break a permanent magnet, you would actually form new north and south poles because the magnetization extends throughout the magnets. It doesn't just originate from the ends. Let me do a demonstration to show this to you. Okay, so now I have my two magnets together, and now they're going to act as one magnet with one north pole and one south pole. So North Pole, the compass is pointing away from the North Pole. South Pole, the compass is pointing towards the South Pole. So the compass is pointing towards the blue and away from the red, because the magnetic field comes out of the red and into the blue, and this compass will always show us what direction the magnetic field is pointing in. So the magnetic field away from the red and towards the blue. Now, so these two magnets are functioning as one magnet with one north pole and one south pole. Now, what happens if I pull them apart? If I pull them apart, I don't just still have one north pole and one south pole. Now I have a north pole and a south pole and a north pole and a south pole. So They each have a north pole, and they each have a south pole. So by splitting this magnet in half, I've gone from having one north pole and one south pole to having two north poles and two south poles. And that same thing would be true if I were to even take this magnet and slice it in half again. I would go from having one north pole and one south pole to having two north poles and two south poles. And as many times as I would slice the magnet, I would still have that situation, because the north pole is not, the magnetism is not just here at the north pole and here at the south pole. The magnetism is all throughout this magnet. It's in all of the little atoms that make up this magnet. Every one of them is a tiny magnet with a tiny north pole and a tiny south pole. Okay, that's our lesson on magnetism, and that is the end of Unit 5. Our next lesson will start Unit 6, which is light. We'll talk about electromagnetic waves and light. Until then, think science.